There is a mine in Western Australia where the rock is so hard and so abrasive that it destroys excavator bucket teeth. It destroys them at a rate that most operations would consider catastrophic. The iron ore formation there was laid down billions of years ago. This rock has a compressive strength that exceeds the design limits of most mining excavators. Standard machines last only months before requiring expensive repairs. The accumulated damage to their structural components requires repairs that cost more than the operation can sustain. But one machine works there without that problem, not because it ignores the hardness, but because it was designed from the beginning to operate in exactly these conditions, to take the impacts. It survives the abrasion and keeps working, day after day, shift after shift, at production rates that make the economics of the operation viable. This is the Liebherr R9800. One of the largest hydraulic mining excavators ever built, with an 800 metric ton operating weight and a massive bucket capacity. Its engineering story is more interesting than its specifications. Liebherr had to rethink fundamental assumptions about how large hydraulic excavators are built. Before we get into the engineering details, we need to understand the world the R9800 was built for. That world operates by different rules. Hard rock mining is different from coal or oil sands. In coal, the material is soft and yields to bucket force without extreme impact loads. In oil sands, it's heavy and abrasive but not hard. In soft rock, blast fragmentation is enough to break material into manageable pieces. In hard rock mining, copper, iron, and gold, the rock retains a hardness that creates impact, loads far exceeding those seen in softer applications. A bucket tooth striking a hard rock fragment generates an impact force that transmits directly into the bucket, the stick, the boom, and the frame. Absorb enough of these impacts, and metal fatigues. Welds crack. Structural members fail. The machine is in the maintenance bay with a crack in its boom. This is the problem the R9800 was built to solve. To be large and survive for its full operational life without structural fatigue failures. Liebherr developed new steel alloys, welding procedures, and structural geometry simultaneously. The engineering investment was enormous, and the result changed what was possible. But that's not even the most incredible part. The Liebherr R9800 has an operating weight of approximately 800 metric tons in its standard mining configuration. 800 metric tons. That is roughly the weight of 550 average passenger cars. All of that mass sits on two crawler undercarriage units, each of which is itself a substantial engineering object. Wide enough to distribute the machine's enormous weight across a ground contact area sufficient to operate on prepared mine floors without excessive subsidence. The bucket capacity of the R9800 is 42 cubic meters in its standard configuration. 42 cubic meters, roughly equivalent to the interior volume of a standard 40-foot shipping container. This bucket is not just a steel container. It is an engineered system with wear protection and structural reinforcement tailored to the material. The bucket teeth are the hardened steel points that make first contact with the rock face. They are consumable items that wear down. In hard rock applications, the interval between tooth replacements can be measured in days rather than weeks. The boom and stick are fabricated from high-strength steel plate, welded into box section structures that combine high stiffness with manageable weight. The geometry of the boom and stick is the result of detailed structural analysis that optimized the arm system for the working envelope. The main frame is the most complex and critical structural element. It must support the upper structure and transmit swing loads to the crawlers. Liebherr's approach involved finite element analysis to identify critical stress concentration points where fatigue cracks are most likely to initiate. They used specific design interventions, larger radii at stress concentrations, additional material thickness, and specialized weld procedures. The result is a main frame that is heavier than purely stiffness-optimized designs, providing the fatigue life that hard rock mining demands. Adding weight to improve fatigue, life has cascading effects. A heavier machine requires more powerful crawlers and more hydraulic flow. More hydraulic flow requires larger pumps, and larger pumps require more engine power, resulting in a larger engine installation. Managing these interdependencies is the central challenge. The R9800 design team successfully ensured the complete machine is optimized for its purpose. What happened when the first units entered service confirmed the decisions were correct. Fatigue cracking problems were absent. The R9800 built today benefits from 2 decades of field experience. It is a better machine than the already extraordinary first units. The R9800 is powered by 2 diesel engines, typically large, high-output units from established engine manufacturers. These engines produce a combined output in the range of 3,000 to 3,500 horsepower, depending on the specific engine specification selected. These engines drive hydraulic pumps that generate the flow and pressure that power every function on the machine. The hydraulic system of the R9800 operates at working pressures up to 350 bar. At this pressure, the hydraulic fluid is not a gentle medium. It is a forced transmission system operating at extreme conditions, and every component must be designed to survive these conditions continuously. Every part must operate without leaks or degradation for the thousands of hours between major service events. The boom cylinders, the actuators that raise and lower the boom, are among the largest hydraulic cylinders in any mobile machine. The cylinder bores and rod diameters are sized to generate the forces required to lift the boom, stick, bucket, and full payload. The sealing systems in these cylinders operate under continuous cyclic pressure variation and must maintain integrity for millions of cycles. The swing system of the R9800 uses hydraulic motors, typically multiple motors in parallel, to rotate the upper structure. The swing is controlled by proportional valves that modulate flow, allowing the operator to control speed smoothly from stationary to maximum. The hydraulic braking system uses the swing motors as pumps in reverse, a form of regeneration that recovers energy and reduces heat. This thermal management feature reduces the load on the hydraulic cooling system and extends the service life of the fluid. The travel system uses hydraulic motors driving through planetary reduction gearboxes to the track sprockets to reposition the machine. The R9800 is designed to stay in one area for extended periods. When repositioning is necessary, it happens slowly and deliberately. The hydraulic fluid management system is designed to maintain cleanliness and temperature within limits required for long component life. Contaminated or overheated fluid is the primary cause of failure. At this scale, a component failure is a major event. Failure means downtime measured in days and costs measured in tens of thousands of dollars, requiring specialized equipment. The filtration system is sized for high contamination capture efficiency, and the cooling system has margin for hot ambient conditions. The monitoring system tracks fluid temperature and contamination continuously, alerting maintenance teams before conditions deteriorate. The hydraulic system's reliability is a function of how well the complete system is managed, how maintenance is performed. Electronic monitoring and control systems are tools that allow the machine to be operated at its potential throughout its service life. The Liebherr R9800 is deployed in some of the most significant hard rock mining operations in the world. In the Pilbara region of Western Australia, home to some of the world's largest iron ore deposits, R9800 units work in challenging hard rock conditions. The banded iron formations are dense and abrasive. Yet, this ore supports construction and manufacturing activity across Asia and beyond. In the copper porphyry deposits of South America, R9800 units extract ore at high altitudes and in arid conditions that test equipment limits. The copper produced here goes into your home's wiring, electric vehicle motors, and the wind farms being built to decarbonize our world. In gold mining, where rock requires careful excavation, the R9800 provides the reach and robustness to make production targets achievable. In application after application, the machine delivers production rates that meet or exceed specifications. Its maintenance costs are consistently lower. Operators spend 12 hours per shift in the cab, reporting a machine that responds predictably and with the consistency they depend on. Consistency means production plan adherence, hitting tonnage targets for customers, investors, and the communities depending on the mine's productivity. But the R9800 is not the end of the story. It is a data point in an ongoing engineering evolution pushing hydraulic excavation boundaries. The next machine in our series is the Komatsu 980E haul truck, the machine that carries what the R9800 digs. A truck with a diesel-electric drive system, completing the production cycle from the excavator's bucket to the processing plant. The numbers are significant, the engineering story is compelling, and we are just getting started.